Hi there, I'm Stefan T. Lauade, and welcome back to the 10th and final part of my video lecture series introducing the standard template library. Today we'll be talking about type traits, which is a powerful way to reason about types and to actually perform computations at compile time. This is the template metaprogramming that you may have heard of. So this month they're actually renovating the Channel 9 studio, so we're in a makeshift studio. So today I only have my laptop to show you code. You'll be spared my horrible scribblings on a whiteboard this time. So first, one of the things when you're working with templates is that it's easy to get caught up in all the angle brackets and lose sight of what you're actually doing. The way that I look at it is, if you think about what computers are actually doing, they only care about bits. They're performing computations on bits, and if you go all the way back to B, which was the predecessor of C, in the B language, there was actually no type system. Integers, floating point, they were all just memory cells. This is so unlike any language today that it's really a foreign concept to imagine no type system whatsoever. If you go to C, C has a type system. It says, okay, if you declare an int, then operations on it will manipulate the bits in so-and-so way. Whereas if you declare it as a double, then operations like plus or times or other things will actually do different things to the bits. So now we're looking at bits through the lens of a type system, through these built-in fundamental types. Now, fast forward to C++, and you get objects. Not only structs, but classes. And these abstract bits even more. Instead of just saying, okay, here's an int, and this represents one coordinate of a polygon, and then here's a double or whatever. Now you can say, okay, here's a collection of bits, and yeah, parts of it is int, parts of it is double, some of it is an enum or whatever, pointers. This overall represents a more abstract concept, like a polygon or an enemy in your game or a font or whatever you have. And the following operations can be performed on this collection of bits. This is that object-oriented programming you've heard so much about. So we've got bits, we've got built-in types, then we've got user-defined types, these classes and member functions and non-member functions on top of them. And this is just successively more abstract. But they're allowing us as humans, who can only fit so many concepts in our head at one given time, to express complicated algorithms and data structures and operations in code. Now, if you look at what templates are doing, they're doing something even more abstract. And this can be confusing. But just hold on for a minute and think about what templates are doing. They exist at a level above classes. And they allow you to say something like, I want to perform an operation if you have a template function, or I want to have a generalized class if you have a template class. That is customizable in some way, usually depending on type, but in C++ you can also have templates on non-type parameters. And this allows us to say things for the first time ever, if you're coming from C, like I want to write a sort algorithm that doesn't really care about the elements that it's sorting. All that we require is a few simple operations, like to be able to compare elements and move them and swap them and whatever. Or you could say, I want a class, maybe a container, that doesn't really care about what it contains. So I could have a vector of int, or a vector of user-defined type, or a vector of shared footer, or whatever. And as long as I can have just a few operations on the type I'm templated on, then I can do very powerful things. I can reuse this code. But it's all happening at compile time, so I'm not paying penalties at runtime for indirection or virtual tables or what have you, especially inhibiting inlining. So templates exist at this level above individual classes. Now, what type traits allow us to do is to inspect types at compile time and then make decisions based on them. So what template metaprogramming is you're writing essentially a little program in a weird language with lots of angle brackets and double colons that allows you to overload functions more precisely. It allows you to write class templates and dispatch based on the nature of the types. You can express things like, I want this function template to be called only if type X is convertible to type Y. Or I want this class template to do something special if T is a derived class of some class foobar. Or I want to do something based on if this type is integral or floating point, or you can perform transformations on types. And so that's what the type traits header allows you to do. This was a bunch of machinery that was originally implemented in Boost. It became part of TR1, so it became available in VC9 SP1. And it's in an even more powerful form in C++OX and VC10, Visual Studio 2010. So that's what I'll be using today. I'll be referring to the C++OX working paper often. This is available on the Standardization Committee's website for free. And the interesting section that you'll want to look at today is currently 20.7 metaprogramming and type traits. And then it lists all of the helper classes underneath. So I'll just collapse this bookmark so you can view this a little better. I can't go any bigger on the font size, otherwise it won't reflow properly. So the hardest thing about template metaprogramming and working with type traits is that you can't debug into it. All of the processing happens when the compiler is running. So if you have a problem at runtime, you can just single step through the debugger and see what memory locations are being modified. And it can be difficult, but at least you can walk through the process. Whereas if you're trying to understand what's going wrong with a template, you can't ask the compiler, OK, I want you to substitute just this little bit of a template, then show me how you did template argument deduction, then show me how overload resolution failed or succeeded or chose the wrong overload or what have you. And this is somewhat difficult. The only way that I found to deal with this is to be able to instantiate templates in your head. And that sounds really scary, but it's really not that hard. In fact, many other parts of C++, especially like initialization and derived classes, inheritance, I find much more complicated. Whereas when you're working with templates, you can imagine that the compiler is playing a series of little games. First, it does name lookup. Then it does template argument deduction. And it will do things like compare the function argument type and compare the function parameter type and try to make them match. And it has a certain set of rules that usually behave quite intuitively for figuring out what types to substitute in there. Then it will do substitution of the template parameters, then overload resolution. This is where substitution failure is not an error, or suffining comes into play. We'll see that in a bit. And then finally, it'll do access control and attempt to actually call what it selected. And with class templates, you've got partial specialization. It's a lot of stuff. And I can't get into all of the core language here, but I will try to cover the very important parts related to type traits. So let's look at a little bit of type traits here. The sort of first types that it has are called true type and false type. And these happen to be typedefs for something called integral constant. That's not so important. What matters about true type and false type is that they are separate types that represent the concept of trueness and falseness. So the fact that these types are separate is very useful. They also contain static values, static const bools, called lowercase value, that are either true or false. So you can either look at them as a type or you can look at them as a compile time value. Both are useful. The reason why these appear in type traits is that many type traits, like is const, is floating point, is integral, is pointer, have nested type defs that are either true type or false type. So this is how you can get yes or no answers at compile time. Because at compile time, we can only work with things like types and static const data members. We can't work with like ints that can be initialized at runtime or anything like that. So the first part of type traits are queries about types. I want to know a specific property of a type, and these can range from quite simple to rather complicated. So if you look at the working paper here, it starts off with these primary type categories. These all represent things in the core language. As I mentioned, is integral. This will return true for things like int, long, short, unsigned char, but not for things like double or an arbitrary class or int star or what have you. You've got is floating point, is pointer, and so forth. So already this can allow you to do some cool things. Let's fire up VS here. I've included the type traits header. Now imagine, and this is somewhat contrived, but this is sort of hello world for the unary type traits. Imagine that I'm writing a template function, sorry, function template. I hate saying template function. Template, type name t, void foo, taking a t, and I want to print t, and like this. Okay. And suppose that I want a couple overloads of this, one to be called for integral types and one to be called for floating point. Well, I can do things like overload a function template on t versus t star, and the compiler will apply certain rules to select the function template that matches either an arbitrary type or a pointer. But there's no way for me, using just the core language without essentially re-implementing type traits myself, to say I want this to be selected for only floating point t versus integral t. With type trace, we can do that. So imagine that foo is going to be my helper function, and I want here, actually let me type integral here versus floating, and I will have this one take true type. What this is a parameter of stood true type. I could give it a name like blah, but I'm not going to use this object. So I'm just going to have a nameless parameter. This is just like I said int, and then didn't bother to give the int name like n. So that's all that's going on there. And then here I can overload this one on false type. So these are just overloaded function templates, nothing too fancy going on there. And then let me write template type name t void bar, take an arbitrary tt, because I'm only going to be calling this with ints and floats or doubles. I'm just passing this by value. If I were passing user-defined types, I would probably want constant references. Again, this is rather contrived. And suppose I want to call foo with t, and then I'm going to pass it whether this type is integral or not. So I'm going to use stood is integral t, and then if I access its nested double colon type, then this will be either true type or false type, depending on whether this type is integral or not. And because this is dependent on a template parameter, and I've got this nested double colon here, I need to say type name. Now, this is a type. I want an object of that type. I'm only going to use it for overload resolution. I'm not going to do anything with it. But because I need a temporary object, I need empty parentheses. The compiler should completely optimize this out because I'm not doing anything with it. Remember, templates, they do things like go in headers, and they're evaluated at compile time. So it's pretty hard to get overheads with them. Oh, I've got a main down here. I've zoomed this in larger than normal, which is why you can't see very much code on the screen at once. And suppose that I want to do a couple foo calls. I'm going to call foo with a completely random number, and then I'm going to call foo again with another completely random number. And there we go. So you can see, I guess I can crunch out some space here. You can see most of this at once. This is what we got. So let me, foo is my helper function. I want to call bar. Thank you, squiggles. I didn't even need to compile that. Okay, this should work. Let's see. And I'm going to compile and run. Oh, it failed. What did I do wrong? League use of this type as an expression. Let's go to line 7. Oh, duh. I'm printing out the capital type T instead of the lowercase t. So you can see here this was actually a template error. I actually don't see a way to zoom in this output. But because it didn't depend on the instantiation context, I just looked at the error itself, and it told me what was wrong. So let me print out the lowercase t there. I'm actually surprised that IntelliSense did not squiggle that. I'll have to report that bug or something. And, I should have hit Control F5. Yeah, again. There we go. So as you can see here, let me scroll up a bit. Come on. There we go. I have my bar that's templated to arbitrary t, and I called it with an integer and then a floating point value, and bar called foo with the result of is integral t, and then that activated overload resolution and selected either the foo true type or foo false type overload that printed out integral or floating. Without type traits, this would have been much harder to do. I would have had to sort of rewrite this machinery myself from scratch, which is possible, but having the type traits header do it for you is very convenient, especially when it comes to the more complicated things like is convertible, is base of, or even the things that cannot be expressed in the core language without special magic. That's one of the things that type traits does. There are certain things that type traits can be implemented with using purely library mechanisms, like detecting whether a type is a pointer or not. Well, I can do that with a partial specialization. That actually is pretty easy. But if I want to detect whether something is a union or the underlying type of an enumeration or a bunch of other things, there's actually no way to get that information from the compiler without a magic compiler hook, something unspecified by the standard that allows the library to secretly talk to the compiler and say, hey, is this thing really a union or not? That's what the standard type traits header does for us, is use these compiler hooks to get information that would otherwise not be accessible. So use type traits. Don't attempt to reinvent this by yourself. So one last thing. Let's look at the code again real quick. Look at what this has done. This has performed an if statement at compile time by using this is integral t type and then using overload resolution on true type or false type. This is template metaprogramming 101. And yet it takes a sort of strange form because we can't just say something like if t is integral. We have to select a nested type def of a template class, in this case a struct, and then pass it to an overloaded function. It looks kind of strange. But once you become used to template metaprogramming, you take one look at this and you say, oh, that's a compile time if statement. So that's why it can look kind of strange, but it's really not so bad. OK, let's shut that down, and let's take a look at some more type traits. Oh, I should press any key to continue. So many simple properties like is something L value reference, R value reference, and so forth. And later on, there are composite type traits. These things don't correspond to the core concepts of the core language, but higher level things like is this a fundamental type, or is this a scalar? Scalar is what this means. You can look it up. It actually has a link here to section 3.9 that'll define what a scalar type is. This one is particularly useful because scalars are things like ints or pointers or doubles, things that are bitwise copyable. They correspond pretty closely to our notion of a built-in type. So it's possible to activate optimizations based on this knowledge. For example, you could have a generic implementation of an algorithm that invokes things like copy constructors to copy arbitrary types. But if something happens to be a scalar or plain old data or integer, then you select a special implementation of your algorithm that does memcopy or memcomp or what have you. That can be faster. It won't work for arbitrary types, but that's why you use type trace to select which implementation you want. The STL uses this rather extensively, and hopefully I will get plenty of chances to show you this in the advanced series that will follow this one as we look into the STL's implementation. So composite categories. Then there are more properties that you can query, like is this type const qualified? Is it volatile? Very high-level concepts like is something plain old data? Is POD? Now, here's a warning. The compiler hooks in VC that these type traits use are usually prefixed by double underscores. Double underscore is POD and so forth. You may see these. In fact, if you look at the STL's implementation, you will see them being used. Please, never, ever, ever use the underlying compiler hooks directly, as tempting as it may be. Always include the type traits header. The reason why is that the compiler's implementation of the hooks, in particular double underscore is POD, is buggy. The compiler has a slightly broken notion of what a POD, plain old data type, is. Fortunately, and in particular, that bug is sufficiently hard to fix that the compiler team has no plans to fix it in the front end. Fortunately, by querying other type traits, the library can actually correct the bug. And by asking, OK, if the type is X or Y, then I know the answer to is POD. Otherwise, if the type is not X or Y, then I know I'm not going to activate this bug. So let's call double underscore is POD. We do all of that horrible work for you in the header. So if you use std is POD from the type traits header, you'll be guaranteed to get the correct answer. If you use the compiler hooks, things will probably explode. Please don't use them. Okay, so those are type properties. Let's move on to the transformations. It's constructible, and that was useful later on. I had to collapse the bookmarks to make this visible, so there we go. Relationships between types. So is same. This is sort of the compile time equivalent of equal equal. This allows you to ask whether two types are the same. I won't write a whole example here, but I can show you a quick sketch of code because I don't have my whiteboard with me. So what is same would look like is this. Let me get rid of main here. Suppose I've got a template, type name T, type name U, stuff, and then I write, at some point, is same T, U, type. This will be true type if and only if T and U are actually the same type. So this will be true for int and int, but not int and double, or even signed int versus unsigned int. Those are different types. So this allows you, and not only can you do things like overload function templates based on this knowledge, you can also use this in class templates. Maybe you want a data member to behave differently, depending on whether a couple types are the same or not. Perhaps you can just directly memcopy between one or the other if types are the same and POD. You can use isSame to detect that for you. So not only can you reason about properties of individual types, but you can also ask for relationships between types. You can also use things like isBaseOf. This one is very clever. You give it a class X and a class Y, and isBaseOf will return true if X is a base of or identical to Y. And this allows you to detect whether this allows you to determine something that is very difficult, if not impossible, for you to write by yourself. We actually use a compiler hook for this one. You can ask whether a type X is convertible to a type Y. We use this in the STL in things like shared putter, where we want shared putter's constructor. If you've got a shared putter T, we want a constructor from a type Y star if and only if we want shared putter T to be constructible from shared putter Y if and only if T star or Y star is convertible to T star. I think I've got that right. Getting that backwards is bad. If it's not convertible, we actually want that constructor to be completely invisible. And for that, we use Sophiony. So let me take a little aside and explain what that means. I have no whiteboard, so let me spell it out. S-F-I-N-E-A-E. What this acronym means is substitution failure is not an error. So imagine, and it's a horrible acronym. It's 6 letters. It's barely pronounceable. And the concept it's conveying is subtle, but it's the best name we got for it. This began life as a feature in the core language that eventually got used for very different purposes than what it was intended for. So let me show you an example. Let me include, because I'm going to want vector. Okay. Imagine I've got a template, and suppose that I need size t. I'm very careful to always include the headers that I need. Template on size tn, void foo, and I want this to take arrays. But let's say that I'm okay with them being arrays of int. I could make this a template, but there's no reason to template on the type here. So I want a reference to an array. We may as well make it const of n elements. And I would like a pointer into that array. So a const int star p. And then I will do something like print out the distance from P to the beginning of the array. So I can do something like array of, I can print out the size. Again, this is highly contrived. I'm just showing you how Stefani behaves. P minus R, I could say address R0 if that would make you feel better. They're actually equivalent. 0. There we go. Ah! I'm terrible at typing on laptop keyboards. Okay. That should hopefully compile. And then, if in my main, I'm just going to collapse these headers here so we can see what's going on. I have something like an array int R is, well, I'll call it A. Int pointer P is address A of, let's say 2. This would be the 33. So I'll expect to see distance 2 printed, of course. Then I'm going to call foo with my array and P. Here I'm just passing a reference to an array if that looks strange. Sorry, I want P. And there we go. Why is it squiggling the 22? That's, oh, duh, this is not an array. Much better. Gotta love that IntelliSense. And let's compile this and run it. This should hopefully work. And it succeeded. Excellent. So here we can see that it has deduced that my array is of size 4. Awesome. And that the pointer is distance 2 from it. All is well and good. This should not be surprising if you have seen templates and references to arrays before. Now, I had included the vector header. Now, let's imagine for whatever reason that I want to do this sort of thing with a vector. So I want to overload foo because I'm going to do the same sort of thing. There's no reason to give it a different name. And let's actually suppose that I want this not to work just for vectors of int, but for other classes like decks and lists and what have you, even std array. So I'm going to template this on a container. And I'm going to take const container ref c, and then I want an iterator into that container. Let's actually make it a const iterator. I know I'm going to need a double colon, so I'm going to say type name c const iterator I. I'm going to print out, I can't spell, container of size, just to prove that we got a real container. Distance I minus C begin. Okay. So I'm going to keep this call here because I'm overloading this. And then suppose that I've got, now I just wrote minus there. That'll only work for random access iterators. So vector and dec and std array, yes. Stdless, no. There's an iterator function called distance that I can use to get the distance between two arbitrary iterators. I'm not going to bother to use that here. Vector of int v, and I'm just going to range initialize this from my array a plus. I'm going to hard code the size that it's 4, and then I'm going to call foo with v, and then I'm just going to give an iterator v begin, and let's give it iterator to the 44, so that'd be plus 3. I expect to see distance 3 printed out. Okay, that looks good. So let's see what happens. I'm just going to snip out some white space here. Okay, that's too horrible to contemplate. Much better. And compile and execute. Okay, and we can see that this worked. I have overloaded my function foo on array versus arbitrary container and pointer and an iterator into that container. And I got container size 4, distance 3, everything is as I expected. However, something very subtle happened here. In fact, substitution failure is not an error happened here. This is the feature. So let's see what went on. The thing is, the compiler does a bunch of things, as I mentioned, name lookup, and then template argument deduction, and then overload resolution and access control. And in particular, something funny happened when we attempted to call foo with the array A and a pointer P. So the compiler is going to do name lookup on foo. It's going to look in global scope, because I haven't used namespaces here, and it's going to see a couple foos. It's going to be like, awesome, I see 2 template functions. Well, the user is probably going to want me to call one of them. I certainly can't call both. So it's going to notice that they're both templates. It's got to do template argument deduction. It's got to figure out, okay, what types do I put in this stuff? So it's going to perform template argument deduction for this first template. It sees that the array is an array of size 4. Yeah, they're ints. So it's going to say, okay, if I choose n to be 4, then this will match. I will have a reference to an array of 4 constants. This matches an array of 4 modifiable ints. It permits constants to be different. So n equals 4. This function is now instantiated with n equals 4, the signature is, and this is added to the overload set. Then it looks at the second function. This is where the magic happens. It sees, okay, I got a foo taking a referenced const c and then something else. Now, there's 2 c's here, but it's only going to perform template argument deduction based on this first one. The reason why is the second c occurs to the left of a double colon. The thing about templates in C++ is that double colons inhibit template argument deduction. They're a brick wall. When the compiler sees a double colon and it sees template parameters to the left of it, it ignores them. It says, I don't know what those guys are. I sure hope that the user told me, or that I'm going to figure it out through other means, because I cannot deduce template parameters that are to the left of a double colon. So this is ignored for the time being. It compares only this const cref c to my array. Now, template argument deduction here succeeds, because as we saw here above, I can have a reference to an array of n constants. So c will be deduced to be array of 4 ints, and then constants will be applied. So template argument deduction succeeded, and yet we know that this can't possibly work. Why? Because let's look at this second function parameter. It's taking c double colon const iterator. When the compiler set this aside, saying, I can't figure out what that c is, I hope I figure it out another way. Well, it did figure out what c is. C is array of 4 ints. Now it substitutes the deduced template argument into this type name c double colon const iterator. What this is doing is attempting to access a nested const iterator type or typedef of an array, a built-in array. That doesn't make sense. Arrays don't have nested iterator, const iterator typedefs. So substitution of the type C into this type here failed. What Safini says is that substitution failure is not an error. What the compiler says is usually if you try to access a nested const iterator typedef of a built-in array, I'm going to give you a hard error saying, you know, what's going on? I can't compile this. Error C, 1, 2, 3, 4, uh-oh. But during template argument deduction and substitution, it's not an error. The compiler, what it does is back out gracefully. It says, okay, you tried to substitute something bogus in there. I'm going to say I'm not going to add that function template to the overload set. I'm going to proceed on as if I had never seen that. So that's what happens. This foo is discarded from the overload set. It's completely ignored because substitution failure occurred. And the compiler looks for other overloads, doesn't see any. It goes back and says, okay, I successfully instantiated the declaration of this one overload. I found that it could take an array of 4 ints. It's the only one. It wins by default, the 2 sweetest words in the English language. So that is why this foo AP selects this overload taking reference to an array of 4 ints. So the right overload was selected. This is the overload that we wanted, but it had to use Safini to get there. You may ask, well, what happens with the vector? In that case, template argument deduction and substitution succeeds for the vector with the second overload because std vector does have a nested const iterator typedef. This is added to the overload set. But template argument deduction fails for this first overload because there is no choice of n that can make reference to n constants, or array of n constants, equal to a std vector. Those types are totally different. So template argument deduction fails for this first overload here, and template argument deduction failure is also not an error, and this is removed from the overload set. So that's why the second overload is chosen for std vector. So that's what Safini is. It's a core language concept that is used, some would say abused, I say used, certainly used differently than that, in type traits. And you can do things like, so what Safini can be used for in type traits is to have extremely fine-grained control over overload resolution by snipping out overloads from the overload set that you don't like for whatever reason. For example, shared putters constructors are removed from the overload set when type Y star is not convertible to type T star. And how that works is yet another type trait that occurs at the bottom. Let me scroll down there. It occurs in other transformations, mostly because they didn't have a different place to stick it. And this type trait is called stood enable if. So this thing looks kind of strange, but now that we've seen how Safini works, it hopefully won't be that strange. It's templated on a couple things. A bool b, non-type template argument, and a second type, by default void, but you can stick any type in there like int or double star or your own type or a referenced int, what have you. And if you look at the specification, this thing has been partially specialized on whether the bool b is true or false. This isn't true type or false type. This is literal bool b true false. It says if b is true, the member typedef type, it shall exist and equal t, the type that you told it. If b is false, then there is no member typedef type. That's kind of strange, but think about what we just saw with Safini. Safini activates, and it says, whoa, I am not, and there's other situations in which it activates, but the usual one is when it tries to access a nested typedef, and that thing does not exist. In that case, Safini activates. Enable if allows you to set this up whenever you want it. If the bool b is true, then you get this type, the type that you want, whatever you passed for t here. If b is false, then the nested double colon type does not exist at all. And Safini will activate whatever thing this occurs on will be removed from the overload set. So this allows me to say things. Let me just show you what it looks like. I won't write a whole example. Erase most of this. Okay. Imagine that I had a foo here, and I'm taking a const ref. Let me make that a t, because I don't want to imply that it's a container or anything. Tref t. If I wanted to use enable if on this for some reason, again, highly contrived, I could say enable if, and then some property of t. Okay, maybe I would like to say is integral of t. Remember that it takes a real bool, so I don't need the nested type, I just want the value. And because it's a nested value, I don't need that type name stuff. That's only for types. And then foo returns void, so I could ooh, look, IntelliSense. I could either use the default void here, or if I wanted foo to return maybe double or whatever, I could have it return double explicitly. I'm going to get rid of this void here. Okay, and then I want that nested type. So I've got to say double colon type. Uh-oh, I said double colon type. I need type name. I have Safini'd this foo. Now I can overload foo on other stuff, and this particular overload will be disabled whenever is integral t is false, because it'll deduce whatever t is from the arguments, and it needs to know the return type of the function. So it will attempt to substitute t into this thing, and we've seen, based on the standard working paper, that if is integral t value is false, then there is no double colon type. Can't have a function without a return type, so that'll be snipped out from the overload set. Enable if is usually applied to return types just because they're so convenient and they're always there. The one place you can't use enable if in return types is constructors. Constructors don't have return types, and yet they can be overloaded. In that case, if you want to use enable if on a constructor, the usual trick is to give them a dummy argument that has a default parameter. So you could have like a void double star, and by default it's just going to be null putter. So the user will never pass anything there, but it still exists for the purposes of Safini. You'll see that in the memory header for shared putter. Hopefully we'll take a look at that in the advanced series very soon. Now, one caution about enable if that I want to leave you with. When programmers first gain the ability to use Safini and to have this extremely fine-grained control over overload resolution, their usual reaction is the power, mwahahaha. And then they go nuts. They start using enable if everywhere. They'll enable if everything because they believe that this is the best way to select overloads that they want. In reality, enable if is a powerful tool, but it's also dangerous. It should not be used lightly. You should rely on things like overload resolution, partial specialization of class templates, partial ordering of function templates, the thing that imitates partial specialization. Rely on that stuff, overload resolution, without enable if as much as possible. You should only use enable if to resolve ambiguities that cannot be resolved any other way, or to prevent completely bogus things from compiling that you want to avoid. This is what happens in shared putter. The Safiny that's applied to its constructors prevents constructors from compiling and interfering with overload resolution when you really want other overloads to be selected. Well, it's rather complicated. I'll just show you what that looks like live in the sources. If you start to overuse enable if and Safiny in general, when you don't really need to, the problem with enable if is because it snips out overloads from the overload set silently at compile time. Remember that whole is not an error part. Then if the wrong overload is selected, you will get a completely mysterious compiler error message. It'll say, I tried to select this totally weird overload that the user probably didn't intend, and it's not going to mention the overload that was really desired and yet was Safinied out for whatever reason, because it had backed out and snipped that thing out from the overload set. You don't get an error message when it happened. Or worst of all, if all of the overloads are Safinied out or otherwise unviable, you will get a weird error message that says, I tried to call foobar, and I didn't find anything. That's very weird because the user who isn't accustomed to all of this template stuff will look at it and say, but I see foobar. It's right there in the documentation. Or they'll go to the header and they'll see, I see 5 different template overloads of foobar. And the compiler is telling me none of them exist. Why? Well, if you Safinied all of them out, that's why. So Safiny is powerful, but it's definitely advanced technique. Don't overuse it. So hopefully this will give you an idea of how type traits can be used. It's sort of a type traits 101. There are many other things type traits can do. They can perform transformations on types. In other sections of the working paper, I can just pop open and quickly navigate to them. There is transformation between types. You can do things, and this is most useful in class templates. You can remove consonants from a type. You can add consonants to a type. You can strip or add pointers and so forth. This can be very useful in data members of class templates. So hopefully now as you're writing function templates and class templates, you'll see opportunities to use type traits and to express things that previously you could not express at all. You've essentially learned a whole mini programming language in C++. So that concludes my intro series to the STL. As I've mentioned both in the comments and in this video, in the next year, 2011, we'll be spinning up an advanced series looking at the STL's implementation, where we use type traits and Safiny and a whole other host of techniques to implement the STL that we all know now and love. And I'll be looking at all of the gory details that power this library that we've learned how to use. See you then.